Section 2.7 exercises. Problem 1. Show that the functions f and g are inverses of each other. If f and g are inverses of each other, then we require that f of g of x, putting g of x inside f of x, will result in the same as putting f of x inside the g of x function, and the result of either one will always give you x, and then you have proved that they are inverse functions. So let's do f of g of x first. So replacing each x in the f function by the g of x function will give us 4 times x plus 7 over 4 minus 7. We can divide out the 4's here and here, giving us x plus 7 minus 7, which results in just x by itself. That alone does not prove they're inverse functions. We must also compose the functions in the other way. So let's take g of f of x, and replacing each x in the g function by the f of x function, we'll have 4x minus 7, then plus 7, and all divided by 4. Removing parentheses, the 7's will cancel out, giving us 4x divided by 4, which also results in x. So we have proved that f and g are inverse functions. Now we're going to find, in problem 2, the inverse of the linear function f of x equals 2x plus 7. So step 1 is to write y in place of f of x, y equals 2x plus 7. Then we wish to interchange the x and y and write x is equal to 2y plus 7. So now solve this equation here for y, and that will give us x minus 7 is equal to 2y, and then dividing both sides by 2, x minus 7 over 2 is equal to y. This new function called y is the f inverse function of x minus 7 over 2. Let's do the same in problem 3 as we did in problem 2, except now we're given a cubic function, 4x cubed minus 1. So we will write y equals 4x cubed minus 1, and then interchange the x and y. So x is equal to 4y cubed minus 1. Now solve this equation for y, and first add 1 to both sides. X plus 1 is equal to 4y cubed, and then dividing by 4 on both sides, x plus 1 over 4 is equal to y cubed, and then taking the cube root of both sides will give us the cube root of x plus 1 divided by 4 is equal to y, and that is the inverse function we seek. Problem 4. Let's find the inverse of this rational function, y equals 3 over x minus 1. Okay, so we write y in place of f of x. Now interchange the value of x and y, so x is equal to 3 over y minus 1. Here, to solve for y, see that it's in the denominator, we will multiply both sides of the equation by y. So we'll take y times x on the left and y times 3 over y minus 1 on the right. That'll give us x times y on the left, and on the right we'll have 3 minus y. Now we need to get both y's on the same side to isolate it and get it by itself. So we'll take x times y, which is already on the left. We'll add y over to the left, and that'll be equal to 3. Finally, factor out the y, so y times x plus 1 is equal to 3, and then y isolated is 3 divided by x plus 1, and that is the inverse function of x. Let's go on to problem 5. Use the horizontal line test to determine if the following graph represents a function that has an inverse function. To have an inverse function, any horizontal line that you can draw on the graph can only intersect the given function one time. And we see that there are many such horizontal lines that we can draw that would violate the horizontal line test. We cannot have two y values for any one horizontal line. So this function does not have an inverse. Problem 6. We have two line segments that give us the graph of a function, and we need to use that graph to then produce the inverse function. First, let's plot those points. So f consists of the line segment from -2, 2, from -2, this should be, this is a minus sign here. That should be a minus sign, that's a mistake. From -2 to -2 here, to -1, 0 there, and then from -1, 0 to 1, 2 here will give us the graph of f. So let's connect those points. There, and then there. And that is the graph of the function for f. To graph the inverse function, we simply interchange the x and y coordinates and plot those points. -2, -2 will result in no change. So this point is also on the graph of f inverse. -1, 0 becomes 0 minus 1 for its inverse function. And 1, 2 becomes 2, 1. And now we connect those points here and here, and that'll be the graph of f inverse. And the graph of the inverse function is always the same mirror image on either side of this 45-degree line, and that 45-degree line is y equals x. Go on to problem number 7. Find the inverse of the quadratic function y equals x squared plus 1, restricted with x greater than 0. This is so that we have an inverse function. So first we will find that inverse function, writing y instead of f of x as x squared plus 1, then interchanging the x and y values, and then finally solving that for y. X minus 1 is y squared, so the square root of x minus 1 is y, and that is the inverse function. Note here, when we took the square root, we used what's called the principal square root and only used the positive square root. And again, this is to make sure that we have a function and its inverse intact with x being greater than 0. So now we have the inverse function. We need to graph both. Why don't we make a table of values for x and y? So here's the original function y. Now x must be greater than or equal to 0. So let's choose 0, 1, and 2. 0 gives 1, and 1 gives 2, and substituting in 2 will give us 5. Now to produce the inverse function, f inverse, which is the square root of x minus 1, we can simply interchange the x and y values to obtain the new ordered pairs on the graph of f inverse. So we'll have 1, 0, 2, 1, and 5, 2. Now we'll take those points and we'll plot each function down here on the coordinate system, and we'll have the graph. So 0, 1 is here, and 1, 2 is here, and 2, 5 is here. So this graph is half the parabola for the function f. So the function f unrestricted is here, and we are only taking the domain to be x greater than 0, so we're taking the right branch. Notice the original function would not have an inverse since it would fail the horizontal line test. So now interchange those ordered pairs. 1, 0, 2, 1, and 5, 2, and there's the graph for f inverse. And notice how nice there are mirror images on the other side of the line y equals x. And that concludes the problem set for section 2.7.